Now, solid solutions have only limited solid solubility. Now, that means in a cooling liquid, the solute or alloying elements will be ejected out of the forming grains into the grain boundaries. So we've got a beaker of water, our aluminium, liquid aluminium, we've melted it. At the freezing start temperature, the alloying element is in liquid form with the aluminium. As the aluminium starts to solidify, the alloy starts to solidify from the freezing start to the freezing finish temperature. The solubility falls off, and excess solute atoms greater than the solid solubility of aluminium are chucked out of the grains. They're pushed out of the grains into the grain boundaries. Remember, we've just said that as aluminium solidifies, there is a mismatch between adjacent grains forming grain boundaries. And in the same way as we solidify an alloy, the alloying elements in excess of the solid solubility, in excess of the sugar that the water can absorb at room temperature, are pushed into the grain boundaries. Let's pause a bit and talk about sizes of atoms. Now, no two atoms are exactly the same size. The atomic radii, that is the size of the atoms, decreases across the periodic table, because as the atomic number increases, the number of protons increases, so does the number of electrons, and effectively the nuclear charge of higher periodic atoms towards the outermost electrons increases. So as the atomic number increases, you get more and more electrons, more and more protons. Remember, the opposite charges attract. So the more protons, more electrons, the charge increases, so the attraction increases, and the atoms actually get smaller with increase in atomic number. That means that the electron cloud contracts and the atomic radius decreases. So the higher the atomic number, the smaller the atoms. And no two atoms have exactly the same size. And this is a schematic. In the middle, we have our wee aluminium atom. On the right-hand side, you've got lithium, a much, much lighter aluminium, lower atomic number than aluminium. And on the left-hand side, you have manganese, a much heavier metal, a higher atomic number. So you can see that no atoms have the same size. The higher the atomic number, the smaller the atomic size. So, and this is a relative, so you can see that lithium, being a light metal, has a very, very large atom. Manganese has a very, very small atom. So no two atoms have exactly the same size. Now, when we solidify a liquid, the alloys of an alloying element, the solvent atoms, are dissolved in the solvent metal, aluminium, on solidification. And on solidification, the solute atoms, copper or iron, alloying elements, substitute into the face-centered cube of the solvent aluminium. Remember, as the freezing start temperature starts, atoms form a face-centered cube, and alloying elements will knock an aluminium out of one of the positions in that face-centered cube on solidification, replace it, substitute it. So the alloying solute atoms substitute for aluminium in the face-centered cube, either in a corner or in the center. So as we solidify an alloy from freezing start to freezing finish temperature, the alloying elements replace an aluminium element in the face-centered cube. And remember, the electron clouds forms the metallic bond between the solvent, the aluminium, and the alloying elements in any position within the face-centered cube and against adjacent face shared faces. So when we alloy, the alloying element replaces an aluminium in the cube within the grains. Solute atoms, the alloying atoms, substitute for an aluminium atom in the face-centered cube, either in the corners or the middle of the faces within the crystalline lattice. Now, remember, no two atoms have the same atomic size. The different sizes of the substituted solute alloying atoms within the aluminium crystals distort the crystalline structure. So silicon is a tiny atom, pulls the lattice together. Magnesium's a middle-sized atom, distorts it lightly, but look what lithium does. Lithium is a very large atom, lower atomic weight than aluminium, and it completely distorts the lattice. Now, the mismatch in the size of atoms causes strain fields much, much greater than the actual atoms. So the lattice is distorted inwards or outwards, depending on the size of the alloying elements throughout the adjacent layers of atoms. Thus, the distortion fields are great. What I'm trying to say is we might have one atom substituted for aluminium, but because that alloying atom has distorted the crystal structure, it is distorting the crystal structure much, much greater than just the one atom. So by putting an alloying element into the crystal lattice of aluminium, we completely distort the crystal lattice. Now, in an earlier module, we said slip. We remember that as we reorientate the face-centered cubes, we find that they are actually planes or lines of atoms, and that we can slip those atoms through mechanical force. Now, the different alloying atoms distort the lattice, and they hamper the free slip of atoms. You can see the lithium there is distorting it. Because to slip over the alloying atoms requires much more force, because the slipping planes have to overcome the distortion or the obstacle of the mismatched alloying elements. So we've got lithium there. We see a simple strain graph. As we try to work and slip the atom, we can see there's a very much greater force required, because to slip the atom, the planes now have to jump over the lithium atom. So physically slip the layers of atoms requires a much, much greater force to slip the atoms over the distortion caused by the mismatch of alloying elements. So alloying elements increase the strength and completely change the properties of the alloy. The alloying elements completely change the nature of aluminium. They completely affect the grains, the structure.